Imagine the tectonic silence of a world long before memory, 1 billion years before humans named themselves, before our first fire, before our earliest myths. The earth breathed in a different rhythm. The sky was thick with carbon dioxide, oceans brimmed with dissolved metals, and life stirred only in microbial form. Yet even then, beneath shifting crusts and rising proto-continents, the possibility of thought might have flickered, not ours, not even remotely human, but some unfathomable awareness rooted in alien biology and unfamiliar logic. What if we are not the first to imagine the stars? What if intelligence, once born, is not a singular occurrence, but a phenomenon that blooms and fades with time's inexorable flow? The unsettling elegance of this idea has become more than science fiction. It's a legitimate thought experiment that cuts across geology, evolutionary biology, and astrophysics. Could a technological civilization have existed on Earth deep in the geological past, only to vanish without a discernible trace? This question is sharpened by the sheer scale of Earth's history. Our species has existed for barely a blink, a few 100,000 years in a planetary chronology of 4.5 billion. If civilizations rose before us, they would have had hundreds of millions of years to emerge, evolve, and be erased. The Earth is a master of concealment. Its surface is in constant flux, erasing what came before. Tectonic plates subduct, taking entire crusts down into the mantle. Erosion scours the landscape. Volcanism melts layers into oblivion. Even the very chemical makeup of rocks can transform under pressure and heat, folding human footprints into forgetfulness. In this context, the idea that we have access to a complete planetary history is profoundly naive. Geological evidence is not a library. It is a palimpsest, a smudged and rewritten surface where only hints of previous chapters remain. Geologists estimate that less than 0.1% of the Earth's history is available in high-resolution detail. What remains are clues, fragments of bones, isotopic ratios, magnetic inversions that offer tantalizing but incomplete stories. Consider the thought experiment known as the Silurian Hypothesis, introduced by climatologist Gavin Schmidt and astrobiologist Adam Frank in 2018. Named after fictional prehistoric beings from the Doctor Who universe. The hypothesis asks a simple but radical question. If an industrial civilization had existed on Earth millions or billions of years ago, would we be able to detect it, not prove its existence necessarily, but at least recognize that something anomalous once transpired, something artificial? Schmidt and Frank weren't hunting for aliens in Earth's crust. Instead, they proposed a methodology to define what traces any technological society might leave behind in the geological record, what they called technosignatures. These signatures wouldn't be monuments or artifacts, not after millions of years of subduction, metamorphosis, and erosion. They would be chemical and isotopic anomalies, artificial concentrations of metals like neodymium or tungsten, Sudden spikes in carbon isotopes hinting at fossil fuel combustion. Perhaps synthetic compounds, like plastics or PCBs, that don't degrade naturally. Even shifts in global temperature curves could carry the fingerprints of industrial activity. But here's the haunting dilemma. Earth's natural processes can produce similar anomalies. Volcanic activity can mimic the carbon spikes of an industrial revolution. Deep-sea hydrothermal vents can concentrate rare metals. So the core question isn't just whether traces might remain, it's whether we'd be able to distinguish them from nature's own fingerprints. To deepen the challenge, consider the lifespan of human constructions. If humanity vanished tomorrow, what would remain in 10,000 years? Concrete would crumble. Steel would rust to dust. Glass would weather into silt. In 1,000,000 years, cities would be buried beneath sediments, and tectonic activity would begin to deform even those. In 100 million years, only subtle shifts in chemical composition, a trace of aluminum here, a smear of polystyrene there would remain. After 1 billion years, Earth would have almost entirely digested us. If the Anthropocene leaves a discernible layer, it will be thinner than a sheet of paper in the stratigraphic record. And yet, we look into the past and expect to find statues, skeletons, or cities. Perhaps that's the arrogance of recency bias. And yet some anomalies persist. The natural nuclear reactors of Oklo, in present-day Gabon, have baffled scientists for decades. Around 2 billion years ago, uranium-rich deposits underwent sustained nuclear fission naturally. Groundwater acted as a neutron moderator. The reactions cycled on and off for hundreds of thousands of years. But what strikes researchers isn't just the process, it's the precision. The geometry of these deposits is eerily optimal, almost as if engineered. Some isotopic ratios remain difficult to explain using purely natural processes. Could ancient beings have stumbled upon nuclear energy? Or did nature itself write the blueprint for what we would later replicate? Skeptics rightly lean toward the latter. But the pattern reminds us that nature and design are not always easy to disentangle. Other clues are subtler. Microfossils dated to 3.7 billion years ago show structural complexity that belies their age. Layered formations, stromatolites, speak of organized microbial life. The Great Oxygenation Event, around 2.4 billion years ago, transformed the planet's chemistry, making aerobic respiration and eventually intelligence possible. But we often forget that life's evolutionary timeline is not fixed. It is elastic. The Cambrian explosion came abruptly. Evolutionary leaps can happen quickly, under the right selective pressures. Could intelligence have emerged during an earlier oxygen-rich period, flourished briefly, then vanished beneath 1 billion years of sediment? We lack data to say definitively, but the gaps themselves whisper possibility. Earth has been through radical climate upheavals, ocean chemistry shifts, and mass extinctions that wiped the slate clean repeatedly. In that silence, in that vacuum of record, speculation becomes a tool not of fantasy, but of humility. Not all intelligence must resemble ours. In fact, to assume so may be one of the most limiting errors in our search for meaning across deep time. When we speak of intelligent life, we tend to picture reflections of ourselves, bipedal creatures with forward-facing eyes, opposable thumbs, tools, language. But Earth's biosphere, in its vast evolutionary experiments, has hinted at other cognitive possibilities. Cephalopods, octopuses, and cuttlefish possess decentralized nervous systems, solving problems with an alien elegance. Corvids and parrots demonstrate memory, planning, and emotional complexity, with brains unlike ours. These are not exceptions. They are reminders that intelligence is not a single path, but a convergence of many. So imagine an intelligence that never needed fire, one that developed in the deep oceans, navigating a three-dimensional world of pressure and shadow. It may have used sonar or electric fields to map its surroundings. Its materials may have been bioluminescent or chitinous. Its technologies enzymatic rather than mechanical. Its communication could have been chemical, visual, or acoustic, not written language, but intricate pulses of meaning layered into waveforms. A society like this may never build cities, but it might still engineer its environment, manipulate genes, or archive memory in forms we fail to recognize. The ocean, with its abyssal plains and anoxic depths, may be the most stable and vast environment on the planet, and also the most elusive. The average age of oceanic crust is less than 200 million years, constantly recycled by plate tectonics. Anything built or buried on the seafloor would not endure. Coral-like megastructures, bioengineered habitats, or distributed intelligence systems could have evolved, thrived, and perished without a single trace reaching us. Even today, over 80% of the ocean remains unmapped and unexplored. We are strangers to the very biosphere that gave us birth. Still, fragments of the ancient ocean remain locked in stone. Sedimentary records from ancient seabeds preserve isotopic signatures of atmospheric shifts, biological blooms, and extinction pulses. But among these, some signatures remain unexplained. The sudden onset of the Paleocene-Eocene thermal maximum, for instance, reveals a drastic carbon release and a planetary warming of 5 to 8 degrees Celsius. Traditional theories cite methane clathrate release or volcanic triggers. But what if, just as an intellectual exercise, this was the footprint of a society that altered its own climate? The Great Oxygenation Event, billions of years earlier, is another such anomaly. Driven by microbial photosynthesis, it transformed Earth's atmosphere from reducing to oxidizing, a planetary scale bioengineering feat achieved by organisms that lacked even nuclei. We call this the work of nature, and rightly so. But it illustrates a deeper truth. Even microscopic life can transform a planet. If such transformations can emerge from unconscious metabolic processes, why not from intention? Evolutionary biology offers further curiosities. The emergence of eukaryotic cells, complex structures with nuclei and organelles, is widely seen as a singular event, the result of a prokaryote engulfing another, which then became the mitochondrion. This symbiosis is not only improbable, it was revolutionary. It gave rise to every multicellular organism that followed. But what if this was not the result of blind chance alone? Could a directed evolutionary intervention, a kind of ancient bioengineering, have accelerated or guided this leap? We already manipulate DNA. We create transgenic organisms, edit genomes, and synthesize artificial chromosomes. In the genomic records of modern organisms, some sequences remain puzzling. Vast stretches of so-called junk DNA persist with no known function. Could some of these sequences carry a signal, a compression algorithm, a blueprint from long ago? The notion may sound speculative, and it is, but it raises a critical point. Information can be hidden not only in form, but in patterns. Consider the possibility of an intelligent species that chose not to leave enduring monuments, but instead encoded its message in biology. A genetic Rosetta Stone, passed from cell to cell, generation to generation, not visible in stone, but replicating within the cells of living creatures. Such a civilization would not need to conquer land. It could colonize the genome. In a way, it would already be among us. The limits of such speculation are governed not only by evidence, but by imagination. When we examine the record of mass extinctions, we notice strange preconditions. The end Permian extinction, for instance, the most catastrophic event in Earth's history, was preceded by geochemical disturbances that cannot yet be fully explained. Carbon isotope excursions, sudden temperature spikes, and disruptions in marine oxygen levels all appear. We attribute these to volcanic activity, perhaps the Siberian traps, but could they also be echoes of something more? To be clear, most scientists reject the idea of pre-human technological civilizations, and the bar for such claims is necessarily high. Extraordinary claims require extraordinary evidence, but the absence of artifacts should not be confused with the absence of influence. If a civilization arose, altered its biosphere, and vanished, would we even know? We look to the stars for signs of life. We scan radio waves, measure exoplanet atmospheres, and hope to glimpse distant technologies. But perhaps the alien intelligence we seek once walked or swam our very Earth. Perhaps its legacy is written not in ruins, but in the chemistry of rocks, in the anomalies of genomes, in the climate's shifting breath. Civilizations do not collapse in a single moment. They unravel, quietly at first. A missing harvest, a fractured alliance, a depleted quarry. What begins as imperceptible stress becomes a structural tremor. From the high towers of empires, the end is rarely visible until it is sudden, irreversible, and strangely familiar. Across the pages of history, from the Euphrates to the Yucatan, great civilizations have succumbed to a common logic. Complexity becomes unsustainable. The anthropologist Joseph Tainter articulated this paradox in stark terms. As societies face problems, they respond by adding complexity, bureaucracies, infrastructures, systems of control. Initially, this strategy works. Productivity increases. Threats are managed. Growth continues. But complexity carries an energetic cost. Each new solution demands more resources to maintain than the last. Eventually, the marginal returns on complexity turn negative. A tipping point is reached, and what once sustained becomes burden. The system collapses, not from an external blow, but from the weight of its own intricacy. This pattern may be more than historical. It may be thermodynamic. The second law, entropy, informs us that all systems tend toward disorder unless energy is continually invested to maintain structure. Civilizations, then, are thermodynamic constructs. They extract order from the environment: fuel, food, metals, information, and convert it into social complexity. But every act of order increases entropy elsewhere. Waste accumulates. Limits approach. Physicist Tom Murphy has proposed that no civilization can grow indefinitely, not only because of resource constraints, but because of heat. If our energy consumption grows at even modest exponential rates, within a few centuries, the waste heat alone would cook the planet regardless of carbon emissions. Growth in a finite environment hits not only material limits, but physical ones. The stars may offer escape, but not immunity. Now apply this logic retroactively. If a civilization once flourished on Earth 2 billion years ago, 500 million, or even just 20 its collapse, would likely follow a similar trajectory. Not sudden apocalypse, but systemic fatigue, a declining energy return on investment, a slow decay of coherence, and then erasure by time. Erosion does not differentiate between failure and forgetfulness. We see this principle in miniature in Easter Island, where a once thriving society deforested its habitat, collapsing under its own monumentality. But the lesson scales. Global civilizations like ours are bound by the same physical constraints. If an earlier society arose, reached industrial maturity, and failed to transition to sustainable practices, its legacy might be no more enduring than ours would be, given a few million years of silence. But collapse need not be only thermodynamic. It could be self-initiated. The development of powerful technologies, nuclear weapons, engineered pandemics, or unaligned artificial intelligence introduces what philosopher Nick Bostrom calls existential risks, thresholds beyond which recovery is impossible. Carl Sagan and Frank Drake speculated that such risks may be universal to technological species, resolving the Fermi paradox not with absence, but with brevity. If a prior civilization on Earth reached such a technological threshold, it might have ended itself intentionally or not. Its ruins, buried in cycles of rock and regolith, might appear to us only as geochemical anomalies, perhaps a sudden spike in rare isotopes, a decline in biodiversity that outpaces known climate trends, or simply silence where activity should have continued. It is tempting to imagine that a sufficiently advanced civilization would preserve itself, but intelligence is no guarantee of wisdom. History teaches us that knowledge often races ahead of ethics. We create power before we ask who should wield it. We construct systems more complex than we can understand, and perhaps, like our ancestors before us, or those before them, we discover too late the cost of what we built. This is not only speculation, it is a model, a predictive framework. If civilizations follow a pattern of emergence, growth, overshoot, and collapse, then the absence of visible predecessors may not disprove their existence. It may be exactly what we should expect. Even now, our own signals, radio waves, data pulses, light pollution are bleeding into the void. But within a few thousand years, without continuous generation, these techno-signatures fade, cities decay, satellites deorbit, servers crash. The echo of our civilization grows faint. And then it, too, disappears beneath the sediment. What remains? Perhaps only what nature itself cannot easily create: isotopic anomalies, redistributed elements, sudden shifts in planetary systems, or a cultural trace encoded not in language or structure, but in the shape of a crisis, repeated. In this sense, the Silurian hypothesis becomes a mirror. It is not just a question about ancient worlds. It is a forecast. It asks what survives, not just of them, but of us. If civilizations fall, as species do, then we are not an exception. We are a phase. And yet, if they rose once, might they rise again? Not all discoveries are made with tools. Some unfold in the mind. Imagine, for a moment, the unearthing of a single undeniable artifact, something unmistakably shaped by intelligence, yet buried in rock 500 million years old. A forged alloy beyond natural metallurgy. A geometry that defies crystalline order. The implications would not merely be scientific, they would be civilizational. We would find ourselves no longer first. The psychological tremor would be profound. In schools, the origin story of humankind would stretch backward, no longer beginning with hunter-gatherers or the first city, but with unknown architects of a lost world. In places of worship, creation narratives might fracture. In museums, the human figure would stand beside the unknowable other, a reminder that intelligence is not singular, nor anchored to our biology. For millennia, we have imagined ourselves as the culmination of a process. Evolution's final stanza, the top rung of the cognitive ladder. But what if intelligence is not a peak, but a plateau? Not destiny, but recurrence. This discovery would ignite philosophy more than it would science. We would ask, if they existed, were they like us? Did they suffer, hope, wonder? Did they gaze at stars with curiosity or calculation? And if they fell, why? We would search their story for patterns, echoes of ourselves. Perhaps their trajectory mirrors ours. An awakening, a bloom of invention, a period of hubris. Maybe they too split atoms before they understood them. Maybe they also built systems so complex no one could fully control them. If their end came from within, would that not be a warning? And if it came from without an asteroid, a supervolcano, a cascade of ecological collapse, what would that mean for us? There is also the ethical weight. If we are not the first, we may not be the last. Somewhere, someday, another intelligence might arise from Earth or elsewhere. Do we owe them anything? A record, a warning, a lesson. Already, efforts exist to mark our era, not just with plastic or radioisotopes, but with intention. The Long Now Foundation's 10,000-year clock, the Arch mission's etched archives, the Rosetta Project's language vaults. These are not monuments. They are messages. They say we were here. We thought. We remembered. Perhaps you will too. But communicating across geological epochs is harder than it seems. Even if a future intelligence decodes our symbols, will they understand our context? If they find our art, will they sense our pain and joy? If they read our equations, will they grasp the fear that hid behind them? We often imagine sending messages into space, but perhaps the real challenge is sending messages through time. This confrontation with the deep past reorients our sense of time itself. History becomes deeper than memory. Civilization becomes a pattern, not a pinnacle. Time stretches like a scroll, not yet fully unrolled, and we occupy only a thin, flickering moment. The idea of previous civilizations also reframes our place in the cosmos. If intelligence arose more than once here, perhaps it arises elsewhere, too. Not rarely, but repeatedly. Perhaps the silence we perceive in the stars is not absence, but the quiet that follows, collapse, or the space between iterations. And yet, there is humility in this view. We are no longer chosen, but we are participants. The stage is wider than we thought, the script longer, the actors many. Our role becomes more precious, not less, because it is not guaranteed. We are not the final word. We are a verse in a larger poem. The existential gravity of such a revelation cannot be overstated. It might shatter certainty. It might provoke despair. Or it might inspire vigilance and care. If we know that others failed before us, perhaps we act differently. Perhaps we take seriously the idea that civilization is not a gift, but a responsibility. Even the idea of collapse changes. It is no longer an apocalypse, but a recurrence. The end of a chapter, not the book. What matters, then, is not just how we thrive, but how we are remembered, and what tools we leave for those who might one day begin again. If the Silurian hypothesis is true, if Earth once hosted others, it changes not only how we view the past, but how we imagine the future. It transforms our civilization into a moment of dialogue across deep time. And in that dialogue, the most important question may not be whether they existed, but whether we have the wisdom to listen. Some questions are too large for certainty, but too urgent to ignore. The Silurian Hypothesis. This bold proposal that Earth may have hosted prior technological civilizations was not born in the margins of science fiction. It was forged in the minds of scientists, precisely because science must probe its own assumptions. At institutions where climatologists model ancient atmospheres and geologists parse the whisper-thin pages of stratigraphic rock, research teams have quietly taken up the challenge. If an earlier industrial society ever flourished and fell, how might we detect its ghost? The tools are precise, the scope vast. Mass spectrometry allows the detection of isotopic anomalies in billion-year-old rock. Rare isotopes like plutonium-244 or technetium-99 do not form in nature, but could be byproducts of nuclear technology. Their presence would be startling. But even more subtle signals may carry weight: a sudden jump in carbon-13 depletion, an unexplained layer of soot or metal concentrations out of geological character. Climatologists turn to proxy data traces embedded in tree rings, ocean sediments, and glacial ice to map ancient climate shifts. The fingerprints of carbon pulses, ocean anoxia, or abrupt methane releases could point to biospheric disruptions. We already see one such pulse, the Paleocene-Eocene thermal maximum, 55 million years ago, marked by an enormous carbon spike and warming event. Its origin is debated: volcanic release, methane clathrates, or something else. But as we dig, our tools confront their limits. The geological record is a palimpsest, a manuscript rewritten endlessly by wind, water, and magma. Most of Earth's crust has been recycled. The deep ocean floor, where traces might have settled, is less than 200 million years old, barely a blink in planetary time. Still, certain structures do endure. The Oklo natural reactors in Gabon, dating back 2 billion years, reveal how self-sustaining fission can occur in uranium-rich deposits. They show what a nuclear footprint might look like after immense spans of time. And they remind us that not all strange signals are artificial. Nature, too, can mimic technology. To distinguish one from the other, researchers increasingly rely on modeling. Could we simulate what a modern industrial society's residue might look like 1 million or 1 billion years from now? What artifacts survive? What changes persist in global geochemistry? These studies give us templates, hypothetical techno-signatures to seek in the ancient rock. But perhaps the most exciting frontier lies in collaboration. Astrobiologists searching for life on exoplanets have begun working with Earth scientists to understand biosignatures and technosignatures. If we can learn to spot traces of non-human civilization on Earth, we improve our odds of identifying it on distant worlds. Conversely, if we spot unusual signals on other planets, chemical disequilibrium, industrial byproducts, it may help reframe what we look for here at home. Some thinkers suggest we look inward too. Genomic archaeology explores the possibility of long-past genetic interventions, editing or engineering. So ancient they have been masked by time and evolution. Could clues to earlier intelligence be buried in biology itself? We must also consider new kinds of memory, not the monument or the fossil, but the pattern, the anomaly, the residue. intelligence, after all, leaves behind more than cities. It rearranges the planet's chemistry. It alters energy flows. It bends evolution around its tools. Those effects may outlive architecture. Yet all this inquiry must balance rigor with restraint. The scientific method demands skepticism, but not cynicism. An absence of evidence is not evidence of absence, but nor is it license for fantasy. Each hypothesis must walk the knife edge, open-minded, but anchored. And as science walks that edge, new questions bloom. Could civilizations evolve underwater, in environments hostile to preservation? Might intelligent life have taken radically different forms? Not building machines, but organisms or ecosystems that acted with collective agency. Would such intelligence even be recognizable to us? The Silurian Hypothesis does not claim to have answers. It invites us to refine the questions. It encourages humility, a recognition that the geological record is not a complete biography, but a fragmented diary with entire volumes missing. In the end, the search for ancient civilizations is not just about the past. It is a mirror. It forces us to reckon with our own impermanence.
Yet stars one of the cosmos' most extraordinary phenomena.
Dispersible.
Lastly, pulsars,
perhaps the
which are
greatest
highly
monument
magnetized rotating neutron
we can
stars
offer
that
the
emit
future
beams of electromagnetic
is not in
radiation,
stone
are also
or
remarkably
steel,
unusual. The precision
but
of
in
their observed
foresight.
pulses, often likened to cosmic lighthouses.
Somewhere beyond the sweep of our immediate solar neighborhood, the Milky Way reveals itself not as a silent arc of stars across the night sky, but as a sprawling system with intricate architecture and hidden depths. 100,000 light-years wide, this galaxy is a continent of stars suspended in a void, its center veiled behind curtains of dust in the direction of the constellation Sagittarius. Light itself, the fastest known messenger in the universe, would take a full 100 millennia to cross its breadth. And yet, in all that vastness, our own sun is just a minor player, situated about 30,000 light-years from the galactic center, orbiting it with measured grace every 200 million years. The Milky Way's visible body is a disk, but this disk is more than a flattened spiral of stars. It is a living, rotating structure, dense with interstellar gas and flecks of microscopic dust that veil and reveal depending on the observer's vantage point. Embedded in this disk is over half the galaxy's observable mass stars of varying ages and chemistries, gas clouds primed for stellar birth, and fragments of dust forged from long-dead stars. Only about 1% of this matter consists of dust, yet that sliver plays a disproportionate role in shaping what we can and cannot see. These dust grains, smaller than a micron, are the ashes of stellar cycles, riding the galactic winds and gathering in the cold nurseries where new stars begin to shine. The Sun, a population one star born from gas already seeded with heavy elements, is one of many in this enriched region of the disk. Unlike its older cousins in the halo, it formed from gas that had witnessed previous generations of stellar death and rebirth. These earlier stars forged elements heavier than helium-carbon, oxygen, silicon, iron, and dispersed them into space. Over time, these materials coalesced into dust grains, then into meteoroids, and eventually into planets. It's from this lineage that Earth itself was born, a world possible only in a galaxy old enough to recycle itself. Circling this luminous disk like a ghostly shroud is the galactic halo, an enormous, faintly populated region stretching nearly 200,000 light-years across. It is not symmetrical or vibrant like the disk. Instead, it is sparse and ancient, a graveyard of primordial stars. The halo does not rotate in concert with the disk. Its stars drift in elliptical orbits, indifferent to the ordered dance below. These are population 2 stars old, metal poor, relics from a time before galaxies had matured. Many are gathered into globular clusters, each a self-contained sphere of hundreds of thousands of stars, all born together over 8 to 15 billion years ago. In these stars, the periodic table ends early. With virtually no heavy elements, their chemistry would not permit the formation of complex planetary systems. In a very real sense, they are orphans of cosmic evolution formed too early, from too little, in an era before stars could build the ingredients for worlds. If intelligent life is to exist, it would almost certainly favor the newer stars, the ones born from richer materials, in denser and more dynamic parts of the galaxy. Between the disk and the halo lies a transitional zone, the nuclear bulge. This central sphere is a gravitational furnace of stellar activity, where population 1 and 2 stars intermingle. The region is so crowded that stars lie hundreds of times closer to each other than in our corner of the galaxy. Dense gas flows here in eddies and spirals, and embedded within this chaos, perhaps hidden beneath the glare of surrounding matter, are the suspected giants, supermassive black holes whose gravitational appetites drive the complex energy dynamics of the core. Star clusters offer a way to measure the distances that separate these structures. Open clusters, loosely bound groups of young stars dot the disk and often cling to their birth clouds for a few million years. The Pleiades and Hyades clusters are close enough for astronomers to calculate their distances through parallax and Doppler-based methods. Globular clusters, on the other hand, are scattered mostly in the halo and nuclear bulge, with precise alignments that allow scientists to calibrate distance scales using brightness and temperature. The Hyades cluster plays a pivotal role in this cosmic cartography. It acts as a yardstick for the galaxy and, by extension, the universe. Through techniques like the moving cluster method and main sequence fitting, its measured distance enables astronomers to leapfrog across space using pulsating Cepheid stars as lighthouses to estimate the distances of remote galaxies. Dust, however, complicates everything. Even the clearest cosmic window is rarely truly transparent. The interstellar medium is thick with particles that obscure, absorb, and scatter starlight. Like fog dimming the view across a field, these clouds can reduce a star's brightness to a fraction of its intrinsic glow. Every 3,000 light-years through the disk, the intensity of visible starlight is halved. Beyond 6,000 light-years, the dimming can make stars appear just 1/4 as bright as they would otherwise be, an effect that masks the galaxy's heart from view. Yet this shroud is selectively permeable. Long wavelength light in the infrared and radio ranges pierces through the dust, where optical telescopes see only a void. Instruments tuned to these wavelengths reveal a roiling, star-strewn core. This central bulge, extending 10,000 light-years from the nucleus, is not a featureless void but a labyrinth of stellar birth and death, of collapsing clouds and radiating gas. Multiple sources of strong radiation suggest something formidable lies hidden, perhaps one or more supermassive black holes, concealed not by design, but by dust and distance. As segment 1 fades, it leaves behind a vision of the Milky Way not as a static map of star positions, but as a dynamic arena of birth and memory, structure and entropy. From the ordered orbits of population 1 stars to the drifting remnants in the halo, this first layer of our galactic understanding sets the stage for deeper questions about cosmic structure, stellar evolution, and the forces that shape everything from black holes to planetary systems. Turn your gaze outward past the boundary of our galactic halo, beyond the reach of our sun's gravitational leash, and the solitary glow of our Milky Way gives way to a spectacle far grander, a universe laced with galaxies. What once appeared to the human eye as faint, cloudy smudges on telescope plates have been resolved into entire star cities. Each galaxy, in motion and in flux, spins its own narrative of birth, transformation, and decay, set within a vast web of structure that challenges our every cosmological model. These galaxies are not scattered at random, like raindrops on a spiderweb. They stretch across the cosmos in filamentary threads and clustered knots. Some are faint, irregular sparks barely distinguishable from globular clusters. Others, like Andromeda or M87, are monumental, their diameters surpassing 500,000 light-years. Most galaxies fall into recognizable shapes: elliptical, spiral, barred spiral, each category a frozen frame from the universe's dynamic evolution. Elliptical galaxies are the most common, making up over 60% of all known galaxies. Their forms are ovoid, smooth, and largely featureless, from the near-spherical E0s to the more elongated E17s. These systems are the ancient vaults of the universe. They lack spiral arms, possess little gas or dust, and contain mainly population 2 stars, ancient, low-metal stars born when the universe itself was still cooling into complexity. Some are mere dwarfs, only marginally larger than star clusters. Others, like the supergiant M87, are monstrous in scale, containing hundreds of billions of stars and harboring colossal black holes in their cores. These elliptical giants often dominate the gravitational centers of galaxy clusters, growing fat on mergers and cosmic cannibalism. In contrast, spiral galaxies like our own wear their age more flamboyantly, with bright, swirling arms wrapping around dense nuclear bulges. They offer a vivid tableau of ongoing stellar life. Their disks are rich in gas and dust, ideal conditions for star formation, and their arms sparkle with the blue-white intensity of young, short-lived stars. These spiral arms are not static structures, but moving density waves, regions where interstellar gas is compressed just enough to trigger gravitational collapse. Newborn stars blaze briefly before fading, leaving behind clusters and remnants that slowly drift away. The spiral arm's longevity presents a paradox. If stars and gas rotated within them as solid features, they would wind tighter and tighter over time, contradicting the loose pattern seen in even the oldest galaxies. This winding problem found its solution in Bertil Lindblad's density wave theory. The arms are not collections of fixed stars, but are more like traffic jams, ripples in space density through which stars and gas pass. This ripple triggers waves of star formation without requiring a rigid structure. The luminous arms are ephemeral, lit by stars that will soon burn out or drift away. But the underlying wave pattern persists, like music played across cosmic time. Galaxies aren't static islands. They belong to groups, clusters, and superclusters. Gravitational associations on scales so immense they defy everyday experience. Our Milky Way is a member of the local group, a modest, irregular cluster of around 20 major galaxies. Its most prominent neighbors, the Andromeda Galaxy and the Triangulum Galaxy, are spirals as well, and the gravitational interplay among them is already reshaping the future. Billions of years from now, Andromeda and the Milky Way will collide and coalesce, forming an elliptical galaxy far larger than either progenitor. Beyond the local group lies the Virgo cluster, a clumpy, irregular swarm of galaxies located about 70 million light-years away. Rich clusters like Virgo contain thousands of galaxies, from delicate spirals to hulking ellipticals. They lack the symmetry of globular star clusters, but exert influence across cosmic distances. Even more massive are the so-called regular clusters, like the Coma cluster, which stretch 10 million light-years in diameter and teem with thousands of galaxies bound together by gravity and perhaps even dark matter. These galaxy clusters are not merely gatherings of stars. They are violent arenas. As galaxies plunge through their environments at thousands of kilometers per second, they interact with streams of intergalactic gas. This high-speed motion through dense plasma can strip galaxies of their own gas, halting star formation and transforming them from active spirals into passive lenticulars. These S0 galaxies, once rich with life, now resemble swept-clean versions of spirals disks without the glow, arms without the pulse. The broader architecture of the universe begins to emerge only when we step even further back. Galaxy clusters themselves group into superclusters, forming a foam-like structure, a vast web where filaments of galaxies are separated by voids spanning hundreds of millions of light-years. Our local group resides within the Laniakea supercluster, which is centered near the Virgo cluster. The structure is gravitationally complex, shaped not only by the visible matter we observe, but also by a scaffolding of dark matter that tethers galaxies into these immense patterns. In trying to understand the variety of galaxies, astronomers have long sought a taxonomy. The most iconic is Edwin Hubble's tuning fork diagram. On one side lie elliptical galaxies, from nearly round E0s to elongated E7s, At the junction are S0 galaxies disk-shaped but gas-poor. From there, the diagram forks into two branches, normal spirals and barred spirals, categorized by the size of their central bulges and the tightness of their arms. Though it was once thought that this diagram reflected evolutionary paths, with galaxies morphing from left to right, or vice versa, modern consensus suggests otherwise. A galaxy's form may be more a matter of birth conditions, density, rotation, and local environment than any smooth transformation over time. But not all galaxies fit the mold. A significant fraction, around 10%, are irregular, defying neat classification. Some are the victims of tidal interactions or galactic collisions. Others are simply primordial systems, never having enough mass to settle into an ordered shape. The small and large Magellanic Clouds, visible in the southern hemisphere's skies, are examples of such irregular galaxies nearby neighbors with chaotic structures shaped by gravitational wrestling with the Milky Way. Here, at the boundary between order and chaos, the story of galaxies becomes one of tension between environment and destiny. Some galaxies are born quiet and remain so, coasting through cosmic time with little disruption. Others are pulled into violent mergers, flung across clusters, or devoured by their larger companions. Yet through all these upheavals, they follow unseen laws, gravity, thermodynamics, and the slow whisper of dark energy stretching the universe like a breathing lung. As we look deeper into space, we also look further into the past. The light from a galaxy 10 billion light-years away left its source when the universe was a fraction of its current age. In that light, we read stories not just of distant structures, but of our own origins. Every distant galaxy is a time capsule, preserving the physics and conditions of an earlier epoch. They hint at a time when galaxies were smaller, more chaotic, and far more prone to rapid star formation. As this segment closes, we find ourselves surrounded by patterns writ large across space, spiral arms and elliptical swarms, dwarf irregulars and giant clusters, all dancing to a rhythm we are just beginning to hear. The universe, once thought to be a scattering of stars, now reveals itself as a carefully choreographed network of galaxies, each a glowing node in a cosmic tapestry. There was a time long before Earth had oceans, long before the sun ignited, when galaxies themselves did not yet exist. No elegant spirals or luminous bulges, no clusters or superclusters to carve patterns across the sky. Instead, there was only gas, a uniform expanse of hydrogen and helium, cooling in the aftermath of the Big Bang, expanding like breath into cold air. But even this early universe, seemingly simple, bore within it tiny imperfections, minute differences in density that would become the seeds of all structure. These primordial variations, less than 1 part in 100,000, were not errors but blueprints. Over eons, gravity acted on them, nudging denser regions to grow denser still. As the universe expanded, the average density of matter decreased, but those slightly overdense regions, protuberances in an otherwise smooth fabric, resisted the thinning. Their relative density increased until, at some critical threshold, they began to collapse. From these gentle perturbations, proto-galaxies were born. A proto-galaxy was not a single object, but a region often hundreds of thousands of light-years across, where gas slowed, halted its outward drift, and began to fall inward. This gas, still composed mostly of hydrogen and helium forged in the Big Bang, was cool and diffuse. Its fate depended on 3 crucial factors: its mass, its initial rotation, and its internal irregularities. In regions with higher mass, gravity pulled more strongly. Where there was rotation, centrifugal force pushed back. And in areas of internal clumpiness, collapse occurred unevenly, giving rise to the earliest generation of stars. These first stars, population 2 stars, were born in the densest central regions of proto-galaxies, lacking heavy elements. They were composed almost entirely of primordial gas. Many were massive, burning their nuclear fuel rapidly and dying in violent supernova explosions. In their deaths, they seeded their surroundings with heavier elements: carbon, oxygen, iron, the raw materials from which later stars, planets, and eventually life would form. This chemical alchemy, repeated across millions of such first-generation stars, enriched the collapsing gas clouds with each cycle of death and birth. As the proto-galaxy collapsed further, a striking phenomenon occurred. The stars once formed ceased to participate in the general infall. Each star followed an orbit around the growing center, but unlike gas, it could not dissipate energy through collisions or radiation. It remained suspended in motion, while the gas continued to sink. Over hundreds of millions of years, this differential behavior sculpted the emerging galaxy's structure. The early spherical swarm of stars, the halo, remained a fossil record of this initial collapse, while the infalling gas eventually settled into a rotating disk. Here lies a subtle insight. The stars in the halo, the gas in the disk, and the shape of the galaxy are not independent phenomena. They are chapters in a single gravitational history, unfolding in time. A galaxy's form, spiral or elliptical, reflects the balance of forces at play during its formation. In cases where rotation dominated, gas was able to flatten into a disk, forming spirals rich in ongoing starbirth. In galaxies where collapse outpaced spin, the result was more spherical, a structure that consumed its gas rapidly, leaving behind a population of aging stars and little fuel for the future. Yet the narrative does not stop with formation. These early galaxies, already differentiated in shape and content, interacted, merged, and evolved. Some spirals collided and formed ellipticals. Some dwarf galaxies were cannibalized by larger hosts. Some retained their integrity for billions of years, like cosmic islands drifting in a sea of expansion. But at the heart of all these changes lay one common force: gravity, ever at work sculpting structure from chaos. Consider a proto-galactic cloud with moderate rotation. As its outer gas collapses inward, the increasing spin creates a barrier. Centrifugal force flattens the flow into a disk. The central region, less affected by this force, becomes a halo. Here, population 2 stars light up first, followed by generations of increasingly metal-rich stars in the disk. Magnetic fields, turbulence, and stellar winds complicate this picture, impeding or delaying star formation. But over time, a majestic spiral emerges, its arms cradling newborn stars, its halo preserving echoes of a forgotten past. Now imagine another scenario: the same cloud, but with higher density and less spin. Collapse occurs more quickly and more uniformly. The gas doesn't have time to settle into a disk. Instead, it feeds an orgy of rapid star formation. With little rotation to resist infall, the gas is consumed before it can spread out. The result: an elliptical galaxy, dense, old, and quiet. Star formation ends early, and the structure remains largely unchanged for billions of years. This dichotomy, disk versus spheroid, spiral versus elliptical, underlies much of modern galaxy classification. But nature, as always, permits exceptions. Intermediate forms emerge. Galaxies with moderate rotation but clumpy collapse may form lenticular shapes. Those with strong initial density variations may fragment into multiple components. And some, battered by collisions or gravitational tides, bear little resemblance to either category, becoming irregular or peculiar in appearance. The process of galaxy formation also invites a broader philosophical contemplation. These structures, vast beyond comprehension, arise not from divine intervention or miraculous design, but from the slow, inexorable unfolding of simple laws. The same equations that govern falling apples and orbiting moons shape the birth of galaxies. Yet from these laws, an astonishing complexity emerges: order, symmetry, beauty. In contemplating the origin of galaxies, we are drawn into a meditation on emergence, how simplicity breeds structure, how chaos gives rise to form. And what of time to us? Galaxies seem eternal, their shapes unchanging across the millennia. But this is an illusion born of scale. Galaxies live, evolve, and die. They merge, shift, and bleed their energies into space. Some lose their gas to intergalactic winds, others collapse into active nuclei. A galaxy that once blazed with newborn stars may one day become a ghost, its brilliance faded, its arms smudged into obscurity. Seen in this light, galaxies become more than astrophysical phenomena. They are timelines, each one recording a different version of cosmic history. Some tell of quiet births and long, graceful evolutions. Others are chronicles of violence, of mergers, collisions, and sudden transformations. And embedded within each is the memory of conditions from a time when the universe was young, denser, and hotter. The current distribution of galaxy types, then, is not arbitrary. It reflects the timing of their formation, the initial conditions of the expanding universe, and the complex choreography of matter under gravity. Fragmentation and aggregation, these two principles, once thought opposed, now appear as partners in a universal dance. From tiny fluctuations in density came the building blocks of structure. From collapsing globes came stars. From the clustering of galaxies came superclusters. And from them, the vast, luminous web that defines our cosmic environment. The very idea that a region with only one hydrogen atom per cubic centimeter, a vacuum by terrestrial standards, could give rise to such richness speaks to the astonishing scale of cosmic processes. What seems empty to us is, on galactic scales, a sea of possibility. What begins as a whisper of imbalance becomes, through time and gravity, a voice shouting across the ages in the form of stars, clusters, and galaxies. In the next arc of our story, we will dive inward again, not into space, but into energy. We will examine what happens when gravity, unopposed, ignites not just stars, but entire galactic cores, turning galaxies into lighthouses visible across the universe, and revealing the monstrous hearts that dwell within. Somewhere in the depths of a galaxy, not in the quiet outskirts where stars drift serenely, but in the violent central furnace where matter crushes into itself, a singular hunger awakens. This is not a star, nor even a cluster of stars. It is a presence invisible, insatiable, and capable of swallowing light itself. At the core of many galaxies, including our own, lies a black hole, not just any black hole, but a supermassive one, containing millions or even billions of solar masses compressed into a volume scarcely larger than our solar system. To encounter such an entity is to brush against the limits of what physics can describe. A black hole is not a thing so much as a region of altered reality, where gravity warps space and time to extremes. But it is not the black hole alone that makes a galaxy's center luminous. Paradoxically, it is what surrounds it, gas spiraling inward, forming a blazing accretion disk heated to millions of degrees that transforms these invisible monsters into some of the brightest objects in the universe. These blazing hearts are what we now call active galactic nuclei, and when they flare to their fullest intensity, we see them as quasars, quasi-stellar radio sources. Though not all are loud in radio, from billions of light years away, they send us signals, not voices, but pulses of energy so vast that for a time, they outshine entire galaxies. They vary in brightness from week to week, sometimes day to day, which means their engines must be astonishingly compact, smaller than the distance from the Sun to Pluto, yet releasing energy equivalent to hundreds of millions of suns. The analogy is often made between quasars and cosmic lighthouses, but that metaphor understates the violence. These are furnaces of annihilation, converting matter into energy with efficiencies unmatched by any known process short of total nuclear conversion. As gas falls into a black hole's accretion disk, it accelerates, collides, compresses, and heats. Magnetic fields twist and snap. Particles reach energies that dwarf anything our machines can achieve. The process is chaotic, yet strangely efficient. Perhaps 10% of the infalling matter's mass is transformed into radiant energy, released across the electromagnetic spectrum. And not all of that energy radiates passively. Some of it is funneled into jets, collimated beams of plasma that shoot from the poles of the accretion disk at near-light speeds, stretching hundreds of thousands of light years into intergalactic space. These jets carve tunnels through the surrounding medium, lighting up radio lobes that balloon like smoke rings around the host galaxy. From Earth, we see them as two lobes of radio emission, straddling a galaxy too distant to resolve, like twin searchlights from some forgotten war. The mechanisms behind these jets are still not fully understood. Some theories invoke magnetohydrodynamics, the same physics that governs sunspots and solar flares, magnified a billionfold. Others suggest that the rotation of the black hole itself, the so-called Kerr metric, twists spacetime, dragging magnetic field lines and launching particles outward. Whatever the cause, the result is spectacular radiation bursts that can last millions of years. shaping the galaxy's evolution and influencing its neighbors. Yet quasars do not burn forever. They flare, shine, and fade. When their fuel runs low, when the surrounding gas has been consumed, blown away by radiation pressure, or ejected by gravitational feedback, they fall silent. The accretion disk dissipates. The jets vanish. The black hole remains, quiet and cold, unless fresh gas stirs it awake once more. The transient nature of quasars suggests that most, perhaps all, large galaxies host supermassive black holes at their cores, and that those black holes go through active phases when conditions permit. In spiral galaxies like our own, the central black hole is often dormant or only modestly active. But in ellipticals, particularly those in crowded galactic clusters, activity can surge. This raises provocative questions. What governs a black hole's feeding schedule? What wakes it? What puts it to sleep? The relationship between a galaxy and its central black hole is not one-directional. While it was once thought that black holes were mere byproducts of galactic evolution, evidence now suggests a deeper interdependence. The mass of a galaxy's bulge correlates tightly with the mass of its central black hole, implying that they co-evolve. Radiation and outflows from active nuclei can regulate star formation by heating or expelling gas. Feedback, in this context, is not a metaphor. It is a literal, energetic coupling between a galaxy's heart and its extended structure. To probe this relationship further is to confront one of the most fascinating frontiers in modern cosmology. Why do galaxies with larger bulges have larger black holes? Does the growth of one limit the other? And what mechanisms ensure this cosmic tuning? Across billions of years and light years, the balance suggests a form of regulation, self-limiting growth, perhaps driven by the same physics that governs planetary atmospheres or ecological systems. In exploring these dynamics, we glimpse a universe where matter behaves like memory. Gas clouds remember the energy they've absorbed. Stars remember the metals forged by earlier generations. Black holes remember every photon they've consumed, storing mass without revealing it. And galaxies, as structures, remember their origins through the quiet echoes of their most violent epochs. But the significance of quasars, AGN, and black holes extends beyond astrophysics. They challenge our philosophical frameworks. Here are entities that cannot be seen directly, yet whose influence is undeniable. They remind us that reality is not limited to the visible, that the most powerful forces in nature are often cloaked in shadow. They are monuments to the limits of our perception and invitations to stretch those limits further. Imagine standing on a planet orbiting a star that once belonged to a quasar-hosting galaxy. In its sky, there might have been a time when night was not dark, when the galactic core blazed like a second sun. The spectacle would have lasted for epochs, longer than civilizations. And then, as quietly as it began, the light would fade. The black hole would remain, silent and unremarkable, as though the fire had never been. These cosmic flickers remind us of transience at scales we rarely consider. They are not just lights in the sky, but chapters in a story of becoming birth, hunger, radiance, decline. They are galactic myths, written in X-rays and radio waves, whispered across billions of years. In the next and final arc of our journey, we will follow these whispers outward beyond galaxies and clusters, into the web of the cosmos itself. We will trace the structures that galaxies form, and explore the frontier where cosmology meets origin, how the universe gave rise not just to stars and black holes, but to the framework of space-time we call reality. The sky above, so apparently empty, is a structure of astonishing complexity. Through the lens of modern astronomy, the cosmos reveals itself not as a scattering of isolated galaxies drifting in random solitude, but as an immense, interconnected web of filigree of matter that stretches across the observable universe, shaped by forces rooted in the earliest instants of time. Clusters of galaxies, each containing thousands of constituent systems, gather into even larger conglomerates, superclusters, bound loosely by gravity and connected by vast filaments of gas and dark matter. These filaments span hundreds of millions of light years, woven together like the threads of an invisible lattice. Between them are cosmic voids, enormous regions of near-nothingness, where only a few galaxies reside. It is this cosmic web that frames the large-scale structure of the universe. Our own local group, a modest collection of about 30 galaxies, including the Milky Way and Andromeda, belongs to the Virgo supercluster, which in turn is part of a still grander structure known as Laniakea, a name that means immeasurable heaven in Hawaiian. But these designations, however poetic, fail to convey the scale. The Virgo supercluster alone spans over 100 million light-years, yet even it is just one among many. As we peer farther into space, we look deeper into time. Light from the most distant galaxies began its journey billions of years ago, when the universe was young and galaxies were more primitive, compact, and chaotically formed. These early structures were shaped by gravity acting on minuscule ripples in the density of matter fluctuations born during the first fractions of a second after the Big Bang. It is within these fluctuations that the seeds of all structure were sown. To understand how galaxies emerged from this primordial soup is to confront a sequence of delicate thresholds. When the universe was just a few 100,000 years old, it cooled enough for protons and electrons to combine into hydrogen atoms. This recombination rendered the universe transparent, allowing light to move freely. We observe this light today as the cosmic microwave background, a faint, uniform glow that fills the sky in every direction. But that calm was deceptive. Underneath the uniformity were those subtle variations, places where matter was slightly more dense. Over billions of years, gravity amplified those imperfections. Matter clumped, gas cooled, and stars ignited. Protogalaxies formed, collapsed, and merged. In some regions, immense concentrations of matter became the cradles of galaxy clusters. In others, matter flowed outward, leaving voids behind. The universe sculpted itself through a dance of attraction and expansion. The competing influences of gravity and dark energy define this process. Gravity pulls matter together, forging structure. Dark energy, the mysterious force accelerating the expansion of space, acts in opposition, driving galaxies apart. Their interplay has defined the universe's evolution since its earliest epoch. At present, dark energy dominates. Galaxies not bound in clusters are receding from one another at ever-increasing speeds. Their light redshifted into invisibility. This cosmic acceleration means that some galaxies we now observe will, in time, vanish from view altogether. Beyond a certain horizon, the so-called cosmic event horizon light emitted today will never reach us. It is not that the galaxies are moving faster than light, but that the space between us and them is stretching too quickly. To observe the universe, then, is also to witness a kind of slow disappearance, a graceful, irreversible fading. And so the cosmos becomes a narrative about presence and absence, about what can be seen and what is forever out of reach. It is a theater of becoming and forgetting. Each star that dies, each galaxy that recedes, each quasar that dims, adds to the silent memory inscribed across space-time. In this context, even the vastest structures become ephemeral. Superclusters are not gravitationally bound holes. Over unimaginable time spans, they too will dissolve. The cosmic web will stretch into filamentary remnants. Clusters will become isolated archipelagos. Eventually, star formation will cease. The brightest lights will burn out, and black holes will dominate the scenery, slowly evaporating, particle by particle, in the cold abyss. This far future is not grim, but profound. It is not the absence of purpose, but the ultimate expression of transformation. The cosmos, from its birth in a flash of light to its slow fade into entropy, is an unfolding of possibility. That it gave rise to galaxies, to stars, to life, and to minds that ask these questions is a reflection not just of physical law, but of contingency, emergence, and wonder. And even here, among collapsing globes of gas and retreating horizons, new questions bloom. Could there be other universes beyond our own observable edge? Might the inflation that seeded our cosmos have birthed others, each with their own laws, their own physics, their own time? The multiverse, once a speculative idea, is now a serious proposition in cosmological circles. Some theories suggest that universes bubble into being like foam, each expanding into its own pocket of space-time. Others propose cycles cosmic rebirths through black holes, bounces, or emergent quantum geometries. In these models, our cosmos is not the only story, but a page in a larger anthology. We do not yet know if these ideas are testable, but they serve a vital role. They remind us that explanations always open into further questions, that knowledge is not an end, but a pathway. Perhaps that is the deepest lesson of the universe. Its immensity is not designed to dwarf us, but to awaken us, to consider galaxies not merely as objects, but as relationships between matter and light, between energy and curvature, between chaos and order, is to realize that the universe is not something apart from us. We are its outcome and its witness. From the spiral arms of our galaxy to the collapsing cores of protogalaxies, from the dust between the stars to the jets of quasar light that travel for eons, we are entangled in this structure, composed of its remnants and guided by its patterns. To know it is to recognize that the cosmos is not merely a place, but a process, and that we, fleeting and fragile, are part of its unfolding. In that sense, the sky is not silent. It speaks through gravity, through photons, through the whisper of hydrogen and the flare of collapsing stars. All we need is to learn to listen.
A star burns in the constellation Orion, a red glow pulsing against the black canvas of space. Betelgeuse, a supergiant 600 light-years distant, has captivated human eyes for millennia. Its light, leaving its surface 6 centuries ago, carries secrets of a stellar life nearing its end. Astronomers watch it now, noting flickers and fades, a rhythm that hints at an imminent cataclysm. This star, 15 times the mass of our sun, has lived a brief, ferocious existence, consuming its fuel in 10 million years, a cosmic sprint compared to our sun's steady marathon. Its surface, vast enough to swallow Jupiter's orbit, churns with heat and instability, a furnace radiating 100,000 times the sun's power. In recent years, Betelgeuse has stirred. It dimmed sharply between 2019 and 2020, losing 2/3 of its brightness, an event astronomers called the Great Dimming. Telescopes trained on its surface saw clouds of dust, perhaps ejected during a massive convulsion, obscuring its light. Then it flared again, pulsing brighter, its cycles erratic. These changes, tracked by observatories like the Atacama Large Millimeter Array, reveal a star in turmoil. Its core, fusing heavier elements like carbon and oxygen, approaches a critical threshold. When it reaches iron, fusion will falter, and gravity will seize control, collapsing the core in seconds. Such a collapse could birth a supernova, an explosion so luminous it might rival the moon's glow in Earth's sky, visible day and night. It would outshine Sirius, the brightest star we know, lingering for weeks, 600 light-years away. Betelgeuse poses no threat. Its gamma rays and cosmic radiation will dissipate before reaching us. Yet its proximity, in cosmic terms, makes it a spectacle humanity hasn't witnessed since the supernova of 1604, observed by Johannes Kepler. That event, 6,000 light-years distant, dazzled Europe's skies. Betelgeuse, 10 times closer, promises a brighter show. The star's rotation complicates predictions. Spinning once every 20 years, its surface moves at 18,000 kilometers per hour, far faster than expected for a supergiant. This speed, measured through Doppler shifts blue light from the approaching side, red from the receding, suggests a past upheaval. Some propose Betelgeuse devoured a smaller companion star, its gravity pulling in material that spun it faster. Nitrogen in its atmosphere, a sign of deep mixing, supports this idea. Simulations show a companion spiraling inward, merging in a burst of friction and heat, leaving Betelgeuse altered. This merger theory reshapes our view of the star's mass. If Betelgeuse began as a single star, it might have 10 to 15 solar masses, destined for a supernova and a neutron star remnant. But a merger could push it toward 20 solar masses, where collapse might form a black hole, perhaps without a visible explosion. The star's distance, uncertain by tens of light years, clouds these calculations. Without precise measurements, its fate remains a gamble neutron star or black hole, supernova or silent vanish. Astronomers trace Betelgeuse's pulses, cycles of brightness spanning 1 year and 6 years, to internal convulsions or a hidden companion. Computer models suggest a star, nicknamed Beetle Buddy, orbiting close enough to tug at Betelgeuse's outer layers. Its gravity could stir the supergiant's surface, amplifying its pulses. Direct evidence awaits the supernova itself, when debris patterns might reveal a companion's influence. Until then, observatories scan for subtle shifts in light, hoping to catch the rhythm of this cosmic dance. Humanity's watch began long ago. Ancient Egyptians saw Betelgeuse as a marker in Orion, guiding their myths. Today, backyard telescopes track its flickers, while global networks of professionals analyze its spectra. The star's youth, 10 million years old, means no rocky planets likely orbit it, their formation outpaced by its rapid burnout. Yet its death could seed the cosmos with elements like oxygen and iron, forging the raw materials of future worlds. As Betelgeuse nears its end, it draws us to the sky, a reminder of stars as engines of creation and destruction. The sky above Orion shifts as Betelgeuse pulses, its red light a beacon across 600 light years. Its behavior flaring, dimming, spinning defies simple models of stellar death. Astronomers, peering through arrays like the Very Large Telescope, see a star stretched to its limits. Its diameter, nearly 1 billion kilometers, dwarfs our sun's. If placed at the sun's center, Betelgeuse's edge would engulf Mars. This scale, measured by interferometry combining light from multiple telescopes, reveals a surface roiled by convection. Giant cells of gas rising and falling, like storms on a distant sea. The Great Dimming of 2019 puzzled observers. Betelgeuse faded to its faintest in a century, sparking talk of an imminent supernova. Data from the Hubble Space Telescope pointed to a massive ejection, a cloud of silicate dust blocking its light. This outburst, tied to a convective surge, hinted at instability deep within. The star's core, now fusing silicon into iron, nears a breaking point. Each fusion stage, hydrogen to helium, helium to carbon, releases less energy, accelerating the countdown. Iron, the final stage, marks the end. Its fusion absorbs energy, starving the core of pressure to resist gravity. A supernova's mechanics unfold in moments. The core, denser than Earth's crust, collapses to the size of a city. Protons and electrons merge into neutrons, releasing a flood of neutrinos, ghostly particles that escape the star, carrying away energy. This implosion rebounds, launching a shockwave that tears through the outer layers. The explosion, brighter than 1 billion suns, scatters elements forged in the star's heart. Betelgeuse's supernova could peak at a luminosity of 2 × 10⁻38 watts, 500 billion times the sun's output. For weeks, it might shine as a second sun, visible even at noon. Yet the star's mass holds the key to its fate. At 15 solar masses, it would likely form a neutron star, a remnant 10 kilometers across. Denser than an atomic nucleus, a teaspoon of its material would weigh 1 billion tons. If heavier, near 20 solar masses, the collapse might not stop. Neutrons, crushed beyond endurance, would yield to gravity, forming a black hole. This singularity, warping space itself, could swallow the star's light, leaving no trace. Simulations struggle to pin down Betelgeuse's mass, as its distance 550 to 650 light-years varies in measurements. The star's rapid spin, 5 kilometers per second at its equator, adds another layer. Most supergiants rotate slowly, their expansion diluting angular momentum. Betelgeuse's speed suggests a violent past. A companion star, perhaps half the sun's mass, could have merged with it millions of years ago. As it spiraled inward, friction heated the supergiant's envelope, boosting its rotation. Nitrogen, dredged from the core, now enriches its surface. A chemical scar of this merger. Such events, rare but not impossible, reshape a star's evolution, pushing it toward a heavier, black hole-bound fate. The companion theory extends to Betelgeuse's pulses. Its brightness cycles, 1 year and 6 years long, mirror a heartbeat. Models suggest a low-mass star, Beetle Buddy, orbiting at a distance where its gravity tugs the supergiant's outer layers. This interaction could amplify convection, driving brightness swings. Telescopes like ALMA search for spectral shifts, hints of an unseen partner. If present, its orbit would imprint on the supernova's debris, a final clue to Betelgeuse's story. Without direct detection, the companion remains a hypothesis, testable only when the star explodes. Beyond Betelgeuse, the galaxy teems with stars on similar paths. Rigel, Orion's blue giant, burns hotter but younger, its supernova millennia away. Antares, in Scorpius, mirrors Betelgeuse's red glow, another candidate for a near-future explosion. These stars, born in clusters, forge elements that drift into nebulae, birthing new systems. Betelgeuse's death will enrich its region, its shockwave compressing gas clouds to spark star formation. Iron from its core could one day form the hearts of planets, a cycle spanning billions of years. The James Webb Space Telescope, launched in 2021, peers at Betelgeuse in infrared, piercing its dust veils. Ground-based arrays, like the Square Kilometer Array, map its radio emissions, tracing gas outflows. Amateur astronomers, armed with backyard scopes, log its brightness nightly, their data feeding global databases. This collective watch, blending professional and citizen science, captures a star at its tipping point. The supernova, when it comes, will flood detectors with neutrinos, light, and gravitational waves, a multi-messenger event rewriting stellar physics. The star's distance ensures safety. At 600 light-years, its radiation gamma rays, X-rays will scatter harmlessly. A supernova within 100 light-years could strip Earth's ozone, but Betelgeuse lies far beyond this zone. Its light, though dazzling, will pose no risk, a spectacle for all to witness. Ancient observers, from Babylonians to Polynesians, charted Orion's stars, unaware of their fates. Today, we stand ready, telescopes poised, to capture a moment that may already have happened, its light still racing toward us. Betelgeuse's glow flickers in Orion's shoulder, a star on the edge of oblivion. Its pulses, tracked by astronomers worldwide, hint at a deeper cosmic rhythm. Beyond its surface, the galaxy churns with stellar encounters, some close enough to reshape our solar system's fringes. A star, smaller than the Sun, passed within 110 astronomical units 11 billion kilometers billions of years ago. This flyby, closer than Voyager 1's current distance, stirred the outer solar system, leaving clues in the orbits of distant objects. Trans-Neptunian objects, icy bodies beyond Neptune, hold these secrets. Sedna, a dwarf planet 937 astronomical units from the Sun, follows an elliptical path, its orbit stretched by an ancient tug. Two others, moving retrograde opposite the planet's motion, defy the solar system's order. Over 3,000 simulations, run on supercomputers, trace these anomalies to a stellar flyby. A star, 8/10 the Sun's mass, grazed the Sun's domain, its gravity nudging icy bodies into chaotic paths. This encounter, 4 billion years ago, also explains irregular moons like Saturn's Phoebe, captured from the Kuiper Belt. The Oort cloud, a spherical shell of comets encircling the solar system, felt the star's pull. Stretching a light-year outward, this reservoir of ice responds to passing stars, sending comets inward. Such events, occurring every few 100,000 years, pepper the inner planets with impacts. Earth's craters, like Chicxulub, tied to the dinosaur extinction, may owe their origins to distant stellar nudges. The flyby's legacy lingers, a reminder of the galaxy's crowded highways, where stars cross paths over eons. Closer to home, the Sun drifts through a vast cavity, the local bubble, spanning 1,000 light-years. This region of hot, low-density gas formed 10 million years ago when supernovae erupted nearby. Their shockwaves carved a void, compressing gas at its edges to birth new stars. The Sun, entering this bubble 5 million years ago, now floats near its center, a cosmic coincidence. Telescopes like Eurosita, orbiting 930,000 miles from Earth, map this bubble's contours, revealing an asymmetry hotter and denser above the galactic plane. A tunnel, carved through the bubble's cooler gas, points towards Centaurus, discovered by Rosita's X-ray scans. This structure links the local bubble to distant regions, perhaps the Gum Nebula or molecular clouds. Astrophysicists propose a network of such tunnels, hot gas channels threading the galaxy's interstellar medium. First theorized in 1974, this idea gains traction as Rosita's data shows the tunnel's edges, glowing with million-degree plasma. The sun's passage through this network shapes its environment, influencing star formation around us. Betelgeuse, too, exists within this galactic tapestry. Its supernova, when it arrives, will ripple through the local bubble, its shockwave mingling with ancient remnants. The star's mass loss, already underway, sheds gas that cools into dust, seeding the interstellar medium. Observations from the Very Large Array show these outflows, streams of carbon and oxygen that will outlive the star. This material, forged in Betelgeuse's core, could collapse into new stars, a cycle driven by the galaxy's relentless churn. The star's variability, its 1-year and 6-year cycles, draws scrutiny. Photometric data, collected over decades, shows brightness swings tied to convective cells, bubbles of gas larger than Earth's orbit. A companion star, orbiting at 10 astronomical units, could modulate these cycles, its gravity stirring the supergiant's envelope. Spectral lines, split by Doppler shifts, hint at this partner, but confirmation awaits higher resolution scans. The supernova's ejecta, if asymmetric, might betray this companion's presence, a final signature of their dance. Humanity's gaze extends beyond Betelgeuse to other stellar remnants. T Coronae Borealis, 2,600 light-years away, prepares for a nova, a white dwarf, paired with a red giant, accretes hydrogen until it ignites, flaring 1,500 times brighter every 80 years. Its last eruption, in 1946, followed a predictable pattern, a brightness spike in 2015, a dip in 2023. Astronomers, alerted by amateurs, expect its next flare soon, a fleeting glow visible without telescopes. Unlike Betelgeuse's supernova, T Coronae Borealis's nova spares the star, restarting the cycle. Its white dwarf, Earth-sized but sun-massive, pulls gas from its companion, triggering thermonuclear blasts. These events, observed since 600 BCE, mark the binary's rhythm. Amateurs, scanning the northern crown, may spot the next eruption, their alerts triggering global observatories. The nova's shell, expanding at thousands of kilometers per second, glows briefly, a cosmic firework in the galaxy's vast arena. The galaxy's edges hide stranger forces, micro-quasars, like V4641 Sagittarii, 20,000 light-years away, mimic distant quasars. A black hole, 6 solar masses, devours a 3 solar mass star, launching jets at near-light speeds. These jets, aligned toward Earth, appear to move 9 times faster than light, a relativistic illusion. The Hawk Observatory, in Mexico, detects their gamma rays, photons at 200 tera-electron volts. These energies, once tied to galactic cores, now emerge from our cosmic backyard, rewriting models of cosmic ray acceleration. V4641, Sagittarii's jets pierce the galactic void, their gamma rays a beacon from 20,000 light-years. These microquasars, compact binaries of black holes and stars, challenge assumptions about cosmic radiation. Unlike supermassive black holes in galaxies like Markarian 231, 500 million light-years distant, microquasars operate on human timescales, their jets flaring over days. HAWC's water tanks, nestled beneath a Mexican volcano, capture these photons, revealing energies 10,000 times beyond typical stellar emissions. This discovery ties local systems to galaxy-scale processes, a bridge between the near and far. Betelgeuse, closer at 600 light-years, looms as a counterpoint. Its supernova, unlike a microquasar's jets, will be a singular event. Its core, now fusing silicon, nears collapse. Neutrinos, streaming from this implosion, will reach Earth first, detected by underground observatories like Super Kamiokande. Light will follow, a blaze visible across continents. The explosion's shockwave, traveling at 10% light speed, will carry iron, oxygen, and gold, elements forged in the star's heart. These will drift, perhaps forming nebulae where new stars ignite. The star's rotation, measured by ALMA's sub-millimeter arrays, remains a puzzle. Its 5 km/s spin, faster than most supergiants, suggests a merger. Simulations show a companion star, one solar mass, spiraling into Betelgeuse's envelope 2 million years ago. The friction, heating gas to millions of degrees, spun the supergiant faster, mixing nitrogen to its surface. This event, modeled on supercomputers, altered Betelgeuse's path, potentially tipping it toward a black hole. Without the merger, it might have followed a neutron star's fate. The local bubble, enveloping Betelgeuse and the Sun, shapes their stories. Formed by supernovae 14 million years ago, its hot gas 10 times hotter than the Sun's surface expands unevenly. Rosita's X-ray maps show a tunnel toward Centaurus, a conduit of plasma linking bubbles across the galaxy. This network, threaded through cooler gas, channels energy from ancient explosions. The Sun, drifting through this cavity, passes star-forming regions at the bubble's edge, their glow visible in ultraviolet. Stellar flybys, like the one 4 billion years ago, connect to this galactic churn, the rogue star, grazing 110 astronomical units, reshape the Oort cloud. Comets, dislodged by its gravity, still trickle inward, some striking Earth. The flyby's influence extends to Jupiter's irregular moons, captured from the Kuiper Belt. Simulations, run at institutions like Caltech, model these encounters, showing how a star's passage ripples through a system. Such events, rare but inevitable, underscore the galaxy's dynamic nature. T Coronae Borealis, in the Northern Crown, offers a gentler spectacle. Its white dwarf, accreting hydrogen, nears another nova. The cycle, repeating every 80 years, follows a rhythm: a high state in 2015, a dip in 2023. Amateurs, scanning with 10-inch telescopes, may catch the flare, alerting observatories like Keck. The nova's shell, expanding at 2,000 km/s, will glow for days. A contrast to Betelgeuse's weeks-long supernova. Its binary dance, observed since antiquity, links humanity's past to its present sky. Primordial black holes, relics of the Big Bang, add a darker thread, smaller than atoms but asteroid massive. They race through space at 25,000 km/s, passing through the solar system every decade. They nudge orbits subtly. A flyby near Mars could shift its path by centimeters, measurable by NASA's orbiters. The 1908 Tunguska event, flattening Siberian forests, sparks debate: meteor or micro-black hole hawking radiation. Eroding these holes suggests they've dwindled, but precise tracking of Mars's orbit could confirm their existence. Microquasars like V4641 Sagittarii tie these threads together. Their jets, mimicking quasars, accelerate protons to near-light speeds, flooding the galaxy with cosmic rays. HAWC's detections, paired with radio telescopes, map these jets, showing a black hole orbiting a star every 3 days. This system, in Sagittarius, mirrors processes in distant galaxies, offering a laboratory for astrophysics. Its photons, traveling 20,000 years, reach us now, a signal of the galaxy's violent undercurrents. Betelgeuse's story weaves through this cosmic web. Its pulses, driven by convection or a companion, ripple across its surface. The 6-year cycle, longer than most supergiants, suggests deep structural shifts. Photometry from the American Association of Variable Star Observers tracks these swings, feeding models at institutions like MIT. The star's dust clouds, imaged by the Gemini Observatory, obscure its light, complicating predictions. When it explodes, its light will flood these instruments, a dataset spanning centuries. The galaxy spins, a spiral of 200 billion stars, each a story of birth and death. Betelgeuse, pulsing in Orion, nears its end, its red light a signal across 600 light-years. Its supernova, perhaps a neutron star's birth or a black hole's silent collapse, will mark a moment humanity may witness bare-eyed. The star's rapid spin, nitrogen-rich surface, and erratic pulses tied to a possible merger or companion paint a portrait of chaos. Telescopes, from backyard scopes to the James Webb, stand ready. Their data a bridge between ancient light and modern eyes. T Coronae Borealis, 2,600 light-years away, prepares a quieter flare. Its white dwarf, feeding on a red giant, will nova soon, repeating a cycle seen in 1946. Amateurs, scanning the northern crown, may spot it first, their alerts triggering a global watch. The nova's glow, lasting days, contrasts Betelgeuse's weeks-long blaze. Yet both tie humanity to the sky's rhythms. Their light, delayed by centuries, reminds us we see the past, a cosmic archive unfolding nightly. The local bubble, 1,000 light-years wide, cradles these stars, formed by supernovae 10 million years ago. Its hot gas and Centaurus tunnel reveal a galaxy threaded by plasma channels. The sun, drifting through this cavity, passes star-forming clouds, their light a faint glow in ultraviolet. Rosita's X-ray maps, built from orbits beyond Earth's geocorona, show this bubble's asymmetry, a testament to ancient explosions. Betelgeuse's shockwave, when it comes, will ripple through this space, joining a cycle of creation. Stellar flybys, like the one 4 billion years ago, shape this cycle. A star, grazing 110 astronomical units, stirred Sedna's orbit in Phoebe's path, its gravity a sculptor of chaos. The Oort cloud, nudged by such encounters, sends comets inward, their impacts etched on Earth's surface. Simulations, tracing these paths, show the galaxy's crowded nature, where stars brush past every million years. These events, subtle but profound, link the solar system to its neighbors. Microquasars, like V4641 Sagittarii, add a violent pulse, their jets, firing gamma rays at 200 tera-electron volts, mimic distant quasars. HAWC's detections from Mexican mountaintops reveal a black hole devouring a star, its light a 20,000-year journey. These systems, scattered across the Milky Way, drive cosmic rays, seeding the galaxy with energy. Their processes, scaled down from galactic cores, offer a window into the universe's engines, a parallel to Betelgeuse's explosive fate. Primordial black holes, Big Bang relics, weave a final thread, racing at 25,000 kilometers per second. They may graze the solar system, nudging Mars's orbit by centimeters. The Tunguska blast, a Siberian mystery, hints at their passage, though meteors remain the likely culprit, tracking asteroids with telescopes like Pan-STARRS. Astronomers seek these ghosts, their influence a whisper in orbital data. If real, they tie the solar system to the universe's dawn, a link across 14 billion years. These stories, Betelgeuse's collapse, T Coronae's flare, the local bubble's tunnels, flybys, microquasars, and black holes converge in the galaxy's dance. Each event, from a star's death to a comet's fall, shapes the cosmos we see. Humanity, watching from a rocky planet, charts this dance with tools and wonder. Babylonians, 6 centuries BCE, saw the same stars, their clay tablets marking orbits. Today, we parse their light with silicon and steel, yet the sky's questions endure. Betelgeuse's light, when it flares, will join this archive, a chapter written in fire,